Hi, Bobby.
Hi. Aniruddhan, I was going through, I was trying to solve some other questions.
Okay.
See, you have shown voltage source, current source, AC, DC symbols, but I see some other funny symbols.
Oh, really? Because I thought we have seen most of what is normally used. Okay, what symbol?
Correct.
So, we use circles
Yeah.
for voltage source with plus and minus for DC.
Yeah.
I think for current source we did like this.
Correct.
Then the other thing we did was AC voltage, and I think we did something like this for AC current.
Exactly.
So, this was VDC, IDC, VAC, IAC, and of course resistor, capacitor, inductor. We have done all of these.
Correct.
Okay, what is that other symbol you saw?
So is, see, there is some square shape but tilted by 90 degree.
Square shaped like a diamond.
Yeah.
Okay. Like a diamond, is it? Yes. Okay. I think I understand. Like this.
And then there is
there's an arrow or something
upward,
like that upward. Okay.
and it's written KIX.
KIX. Okay. Something like this.
Yeah.
Okay. And like this, right? Oh, okay. Now I understand.
What is that?
So this diamond symbol represents a different kind of source, current or voltage source.
Means?
I've also seen voltage sources like this, right? I think you may also have seen this with a plus and minus inside.
Correct.
Maybe it might say, I don't know, K times Vx maybe, or something like that, right? Well, so in basic circuit theory, so these sources, DC, AC with the circles, they are all classified as independent sources.
Means they don't depend on anybody.
They don't depend on anything or anybody, right? So if you have a 12 volt DC,
it's 12 volts.
It's 12 volts. The potential difference between the two terminals is always 12 volts. Same thing for IDC. If it's a current source of 2 amperes, the current going through it pushes from one terminal and pulls in from the rest of the network in the other terminal 2 amperes.
2 amperes.
Nothing can change. That will never change. And same thing for AC also. But these are called dependent sources. That is why you have this K times IX. That IX probably means something. We'll see. Okay. So these would be classified as dependent, or sometimes some people use controlled.
So value of this current or voltage, etc., depends on something else.
Depends on something else. Correct. So if you had a DC current of 2 amperes, for example, it means the current is 2 amperes.
Correct.
But here the current is K times IX. IX is the current flowing somewhere else, because I is normally used for a current variable. It is some current flowing through some other branch of the circuit.
Okay.
So it is not constant. The current through this depends on the current through somewhere else. So this is strange, right?
So did you say this is used somewhere else? Or?
Yes, actually this is very useful. Maybe the students will use it. Towards the end of this course, we will see what are called electronic circuits. So as you see, this course is called Electrical and Electronic Circuits.
Okay.
This is used in electronics. And they will start learning electronics in this course.
Then this becomes
clear. This is, I think most likely they will use it in a future course.
Okay.
There will be an analog electronic circuits course where they'll use it a lot.
So then it is better to know how to deal with this.
Correct. We should teach them right now.
Okay.
So maybe we'll just do it. Okay. So I see that you have we have drawn K times IX and K times Vx. Okay. So the current through this current source. Do you see any other kind in the textbook? You must have.
Something else.
Okay.
Again, voltage source marked as R into Ix.
Okay. So voltage source is R into Ix. Okay. Of course.
Yeah.
Makes sense. Yeah. And then now I can also imagine something here.
G into Vx.
G into Vx. Okay, makes sense. So current source. Okay, so perfect. I think that makes sense. There are actually 4 types of dependent sources, control sources. So in fact, as we can see, you can either have a current source or a voltage source. So you have both kinds, and the controlling variable can be either the current through some other element, through some wire somewhere, or the voltage between two nodes somewhere.
Okay.
So now you have 4 different types. So maybe shall we write down the name of each one of these?
Yeah, but I think I have some clarity.
We have some clarity, right?
See, anyway, your symbol is very clear. Source shows current.
Correct.
It depends on something in the circuit.
Correct.
So with this, I think I can manage.
Can you tell me, can you guess what the name would be?
I don't know.
You have just said it, except in the sentence we should just remove all the verbs and all everything.
Current control current source.
Perfect.
Oh.
So this would be also abbreviated as CCCS.
Okay.
Or a current controlled.
So it's a current source. It is controlled by another current.
That is correct.
Okay.
And now I think we can all guess. We can all guess what everything is. So this
is a voltage source again controlled by another voltage.
Another voltage. So voltage controlled voltage source. Okay. And I don't need to write down everything.
Yeah.
So people, in fact, when they talk, no, they just say CCCS, VCVS, and so on.
Okay.
So voltage control voltage source. Okay. Then this would be
current controlled voltage source.
Current control voltage source. So CCVS.
Yeah.
And then let's say this last one is it's a
voltage by a voltage.
Correct. So voltage control current source. Okay. I think now students can see there are 4 different kinds of elements. So I think they will use it in electronics, but we will introduce it to them as some kind of ideal element like what they have here, right? Great.
Okay. So then maybe we should try some examples.
We should. We absolutely should.
With this element.
With this element. Correct. Let's do it. Well, actually, I just wanted to point out before we go there,
please.
2 things. I just realized that the textbook has said R times Ix. Most likely because you are getting a voltage, you are multiplying this is the controlling variable is Ix. You need to multiply it with something to get this voltage. It must be a resistance.
So that the unit has to
unit has to match. So electrical engineers, especially circuit theorists, are very specific about units and using the right variables.
Correct.
Right? And also using the right symbols also.
Yes.
Right? These are all very important because it avoids confusion for everybody.
In fact, this is our language.
Correct. So, I noticed K is okay because it is just current by current. So, K is a very common variable for some unknown constant. Now, I noticed this G. So, any guesses what G could be? Because I don't think the students, they must be wondering why
so
K.
From the voltage, if I have to get current, G has to be 1 by R.
1 by R, correct. So, in fact, G is just 1 by R. So, right, it is like an inverse of a resistance. Because you need to multiply something with a voltage to get the current. So, this is Ohm's law.
Yeah.
Right. So, we could have just written I equals V by R.
Yes.
Now, people just want to write it as G times V. So, it is just the inverse of the resistance.
Okay.
And you can guess what G is called also. Because conductance. Because the resistance resists, right? The inverse of that, they call it, it allows it to conduct. Super. So, conductance.
Okay.
And we can also define now, this is for DC. You have control sources for AC as well. Why only for DC? You can also have AC control sources, right? So, just like you have VDC, IDC, VAC, IAC, if you have an AC network with a CCVS or a CCCS and so on, the controlling variable can be a phasor.
So, it will be very similar.
Except
that the symbol instead of plus minus, it may be a...
It may be like a AC sinusoid or something.
Okay.
right? And also, now that we have introduced conductance, maybe we should introduce a little bit more, because we talked about AC and conductance.
Yeah.
Now people may be interested to know what will happen if you have a Z instead of R.
Oh.
Maybe we'll quickly define that as well.
Yes.
Huh?
Good idea.
So, so suppose you have some R, well, we'll just use some unknown, right? So this is some Z, which is R plus Jx. And we said Z is the impedance.
Yeah.
So that's the way we defined it. Z is the impedance. We said R is the resistance. And X is the reactance. Right?
Yes.
Now we talked about inverse of resistance as conductance. Now what happens if you have R plus Jx? Students must be wondering, if you have AC circuits, you might have inverse of impedance.
Impedance also.
So 1 by Z. And that is also a complex number.
Correct.
Right? So electrical engineers have a special symbol for that as well, because they like to use. So they will call this Y. Right? You can see slowly you are using up all the variables towards the end of the alphabet. You had Z, X was used, so they decided why not use Y, I think. So this will also be a complex number. They need to have something plus J something, right? So one thing I realized is that if X were 0, this is purely resistance.
Then it is conductance.
Then it's just conductance.
Yeah.
So most likely it makes sense to have the real part as conductance.
Yeah.
And the imaginary part is, so this is conductance. The imaginary part will be something else. It will correspond to the imaginary part of the complex number. That is represented by the symbol B, right? And that is called the susceptance.
Okay.
So
so Y is
admittance. Y is admittance. Again, same idea. In the resistance, we said resistance resists the flow of current.
Correct.
Inverse of that, it allows current to conduct. So conductance.
Correct.
So what they decided was, I think, impedance impedes the flow of current. Now Y admits current. That is what I feel. I always used to feel nobody defined this for us, but I think that is how the name must have come up.
It's a good way to remember also.
Yes. So Y, the inverse of Z is called admittance. And G is the conductance.
Yeah.
And B is called the susceptance. They have some, in English they have some weird spelling, SUSCEPTANCE, I think, susceptance, I think. So one more really important thing we have to always keep track, ohms, unit is ohms.
Okay.
This unit R was also ohms, right?
Yeah.
G, yes, we need to come up with a new unit.
Flip the ohm.
Flip the ohm, right? So, and what is the name? You also flip the name also, right? So, lot of people, at least earlier circuit theorists used to use mho. I think it was just inverse of ohm, right?
Correct.
And they flipped the symbol also. But lot of electronics people also use the SI unit is not mho, apparently. I read in a textbook that the SI unit is capital S. Siemens.
Correct.
Right? So this mho is what circuit theorists use, but technically you can also use S, which is the SI units, which is Siemens.
Capital S or?
Capital S. Because I think the SI unit, small s is seconds, time.
Correct.
So you have to not get confused, so capital S.
Correct.
So this is, I'll write it big. I'll show that this is capital S.
So we have conductance. Conductivity, if I have, I can calculate conductance.
Conductivity, if you have, you can calculate conductance. That's right.
So this resistance, you used to say rho L by A. So
Correct.
If we have a,
that's correct. So that's how we started. So your resistance.
if I have a rho
so if you have, how shall we do it? So shall we show it like this? So maybe I'll show it like this.
Yeah.
If you have a conductor like this,
Yeah.
No, I'm not drawing it correctly.
Correct.
Like this and like this. So if current is flowing like this and coming out like that, like that, no, from the center.
Correct.
And if this was, let's say, A and B, or X and Y, shall we say, X and Y, and the length was L. So the cross sectional area,
we'll just shade that area.
We'll just shade that area. Right.
So that's the area through which the current is passing.
Correct. That's the area through which the current is passing. So the idea is that the current will automatically, for a uniform conductor of this area, the current will just uniformly distribute in that area. So the cross sectional area is X times Y, and the length of the conductor is L. So the idea is that the resistance would just be the given by this expression, rho L by A.
Rho is resistivity.
Rho is the resistivity. L is the length. So of course it makes sense, no? If you use a longer wire, you will have more resistance. And if the cross sectional area is larger, the current will distribute over a larger area, so it will be easier for the current to flow. That is the basic idea. And rho tells you something about the material. So L and A are the properties of the dimensions, but rho is a property of the material.
Okay. So if it's copper and gold.
Okay. So same dimensions. Copper is more conductive, so you will have lower resistance for copper, no? I think.
Or we will take more easier to differentiate.
Yes, easier to differentiate example. So maybe, well, you can just use iron and copper. Right? So copper is much more conductive than iron. That is obvious. You are right. Gold, you have to be careful. But I remember checking long ago. I think copper is still more conductive than gold. That's what I vaguely remember. We should check.
That is assignment.
That is assignment. They can check. Correct. So.
Okay. So this rho, and we were talking about conductivity.
We are talking about conductivity. Correct. So this is the resistance. So now the conductance for this would be the inverse of this, no? So I think that's why we started with this.
Okay.
So it will be by A by rho times L. But so let's maybe define it, no? So this is the resistivity. This is the resistivity. So the conductance is of course dependent on A by L, but it is now proportional to inverse of the resistivity, and that is what we call conductivity.
Okay.
So this would be the conductivity.
Sigma. Okay.
So I think now
since we said this much, maybe the same element, let's say if it's a nichrome wire or something.
Okay.
Nichrome is a resistive.
It's an alloy, right?
Correct. So if the temperature increases,
okay,
then the resistance will remain same, or?
Oh, it will definitely increase, right? We know that. Well, it will definitely change.
Correct.
We should be a little bit careful, right?
Correct.
So maybe we can tell them a little bit about that as well, right? So
I heard about something called temperature coefficient of resistance.
Correct. So let us say there is some resistance R, we have a resistor, and there is some temperature T, right? So let's say if you were to plot the value of the resistance as a function of temperature, so let's say Kelvin, this is in ohms, let us say. Now if you take an ideal resistor, you will only have some flat
with respect to temperature,
right? Even if you change temperature, resistance will be flat. But most materials, no, I can already see, no, so a whole bunch of things will happen.
Correct.
I am trying to imagine the first example we took. I think we took the example of rectangular cuboidal conductor, X and Y and L, no. So we said that L and A, so automatically I can imagine maybe there is some expansion or small dimensional changes. So that is one possibility. But I can also imagine that this resistivity may be a function of temperature, right?
Yes, because the electrons will be behaving
differently. Correct. So
they
start vibrating. So the way we were taught in semiconductors was that you are trying to, when you are trying to apply a voltage and pass current. So what is happening is you are trying to measure how many electrons are entering here and leaving there. Correct. So it's in one direction. Correct. Whereas inside the conductor, there are so many electrons that are just there, right? Yes, yes. They are not necessarily, not all of them are moving. And if you increase temperature, then they will normally, maybe they'll stay there, but they'll get more energy, right? So most likely, I can imagine if you want to send one electron from one side to the other, if there is vibration of electrons, the chances of the electron reaching the other side is lower.
The resistance is more.
Resistance is more. Okay. So normally I would imagine that many materials would do something like this. Well,
most of the conductors.
Most conductors would do something like that. In fact, I have shown it as a straight line. We don't know, right?
Yeah.
Mostly it is straight.
Yeah.
In semiconductors, in electronics, they will learn later.
It's not.
It's highly nonlinear. Yeah. But here we will just assume it is a straight line.
For the metals, maybe we can.
Correct.
Yeah.
Correct.
So that will. So the resistance will become some R naught into.
Correct. So let's just call this R naught.
Yeah.
So this is the resistance R naught. Well, we can just model this. You are right. So we'll call this.
If you know the slope.
Yes, if you know the slope. Correct. R naught into 1 plus, what is a good symbol to have? Alpha, we'll use alpha.
Yeah.
Okay. Alpha times T.
Yeah.
Like this. Okay. So the slope is alpha, right?
Correct.
So.
Okay.
Yeah.
So, nice.
Yeah. Oh, there are also materials, specially designed materials, which can have a negative temperature coefficient also. That is, those kinds of materials, at least over certain temperature ranges, are also available. I have heard of some things. They experiment with a lot of materials, alloys, maybe combinations, where in some, maybe in some region, maybe in some range of voltages, it might have negative alpha, right? So that also I have heard of. So they should not think that everything has only positive alpha. Yeah. There might be negative alpha also.
And some material with very, very low alpha.
Yes, so that is also possible. A third set of materials, you may just have like this, right? So that is also possible.
Yeah. I think even for copper, it's 0.003 or so.
That's right. That's right.
I remember something called Conductance.
Yes.
So many zeros are there.
Okay, I see.
Another assignment, maybe they can.
Maybe they can investigate and find out.
Yes.
Correct.
So from
yes,
voltage, I mean,
we came a long way. Maybe we'll work our way back.
Yeah.
So here they understood what resistance is, and resistivity is there. Conductance depends on conductivity, right? We came to that because we were looking at this.
Yeah.
So we need to write down the units, no?
Yeah.
I think that's where we are stuck. So this is one common unit. This Siemens is another common unit, capital S. Either of these two, Mohs or Siemens. So I have noticed in olden day textbooks, Mohs is very common.
Correct.
But in newer textbooks, they are trying to encourage people to use the SI units. So a lot of people I see using the Siemens.
We are supposed to use.
We are
supposed to use
SI units. Yes. That's right. Yes. So we are supposed to use SI units. So we'll assume. Don't be surprised if you see Moh.
Correct.
So that's all. We should just make sure, because if they pull up some old textbook to do some examples, if they say Moh, they'll be like, what is this? Printing mistake. Correct.
Now this admittance, etc. Is it good for, I mean, will it help somewhere particularly?
Let's see. So we are doing 1 by Z.
If I have R plus JX, that looks simple. Now if you do 1 by of that, it's going to be
it is going to be very more complicated, right? Well, it turns out that it is. Because, well, let's look at the series and parallel that we did a long time ago, right? So if you look at two resistors, no?
Correct.
If you put them in series, so let's say R1 and R2. Suppose we put them in series. We know that the total resistance, so R equivalent is R1 plus R2.
Yes.
And if we put them in parallel, so this R equivalent we know that it is R1 R2 by R1 plus R2.
Correct.
But the way we got this was not like this when we solved it.
It was, yeah, true.
Correct? So maybe what I will do, I will write it like this. I will take the inverse of R equivalent. You can see that it is R1 plus R2 by R1 R2. So that is just 1 over R1 plus 1 over R2.
Okay. So this is conductance.
This is actually conductance. So the equivalent conductance is simply the sum of the two conductances. Okay. So if you have resistances in parallel, the effective conductance is the sum of the two individual conductances. Because this would have been written as 1 over R1 plus 1 over R2. I think that's how when you solve the equations, that's what it gives us. We kind of simplified to this and started using this.
So generally, if we have parallel circuits,
this
admittance,
etc. is very easy. Correct. And you will see the same thing for admittance as well, you are right. So if you have G plus JB form, it will be very useful if you have them in parallel. So, but if you use conductance in series,
unnecessarily it is complicated.
It's complicated because you will get like this: 1 over G equivalent will be 1 over G1 plus 1 over G2. It will be exactly like what you had originally for the resistors. Complicated.
Got it.
And we will say the same thing just for completeness, no? So we will say that if you had two impedances, same thing is valid. And probably the students should go and check it for themselves. So if you have two impedances Z1 and Z2, we will just tell them that in parallel, the equivalent Z is going to be Z1, Z2 by Z1 plus Z2 in complex form.
Correct.
But what we can tell is that the equivalent Y will be 1 over Z1, which is Y1 plus 1 over Z2, which is Y2. Again in complex form. So the admittance, when you have circuits in parallel, admittance is very easy.
Understood.
That's right. In fact, I think in the maximum power transfer lecture, we did some experiments where we had a resistance and an inductance in parallel and so on. Maybe might have been easy if we had calculated the conductance and tried to calculate it. I think the students can try it out. If they see any previous examples or new examples, they can try it out. Yeah. So we are going back now, right? So we came to admittance. The reason we came to this was because we got the conductance.
Okay. So from here you went to...
We went in a big tangent, no? Completely different direction.
Useful.
Very useful, very useful.